Okay, so I'm going to tell you how to find the nth roots of any complex number, a plus bi. And this is kind of a central point of this topic. Any complex number, including one that's purely real or purely imaginary, um, has nth roots. So if I ask you to find all of the 75th roots of a particular number, first thing to recognize is there are exactly 75 of them, and there are 75 different ones. So it's not like there are some numbers that have only one square root or some numbers that have only 40 80th roots. Any number has 80 80th roots, and that's just how it works. So this is how you do this. So first of all, take the number a plus bi and convert it into the form r e to the I theta. We've seen earlier how you do that. You simply map the point a plus bi onto the plane and then find its polar coordinates to get r and theta, and then just write it in that form, r times e to the I theta. The next thing you want to do is find the real nth root of r. When I say that, I mean r, which is the radius, is always going to be a positive real number. So that number is going to have one, at least it's going to have at least one positive real, it's going to have one positive real root. So it may have more than one real root depending on what n is, but it's going to have one positive real root, and that's the one that you want to find. In fact, I'll put in here that you want the positive one. So the next thing you're going to do is divide theta by n. So you've got some theta that tells you where the object is on the complex plane, where the number is on the complex plane, and you're going to divide that by n. That is going to be the angle of the first, that's going to be the angle of the first of the roots. And then what you're going to do is you're going to keep adding a fraction of the unit circle to that angle. You're not going to change this, you're not going to change the new radius of the root. You're just going to keep changing the angle. So all the roots are going to lie on the same circle whose radius is nth root of r. That's why you calculated this number up here. That's going to be the radius of the roots. And you're going to start with theta over n as the angle of the first root, and then you're going to keep adding 2 pi over n. In other words, 1/nth of the way around the unit circle until you get to all the roots. Okay, so we're going to do an example. Let's find all the fourth roots of negative 5. So first of all, how many fourth roots of negative 5 are there? There are 4 of them. So let's start by writing negative 5 in exponential form. So we know that negative 5, which by the way is a complex number, it's it's negative 5 plus 0I. So negative 5 is equal to 5 e to the I pi. So this is going to allow us to find all the fourth roots of negative 5. So the first thing we want to do is we want to find the positive real fourth root of 5. Well, all we can really say about that is that the positive fourth root of 5 is just 5 to the 1/4. That's as good a way as any to write the positive real root of 5. What is this going to be? This is going to be the radius, or we'll also call the modulus, of all the roots. Because recall that all the roots lie on the same circle, so they're all going to have the same radius. Next thing we're going to do is we're going to take pi and divide it by 4. So this is going to be the angle, or argument, of the first of the fourth roots. Remember, there are 4 roots. One of them has to be the first one. The first one is going to have that angle. So let's write the number 5 to the 1/4 times e to the I pi over 4. This is the first fourth root of negative 5. Okay, now, first of all, let's just convince ourselves that this actually is a fourth root of negative 5. If it is, then that means that if I take this number and raise it to the 4th power, I should get negative 5. So let's just check this out. Let's just verify that that is in fact one of the fourth roots. 5 to the 1/4 times e to the I pi over 4. I'm going to raise this to the 4th power and see if I get negative 5. If I do, then that means that that was one of the roots. So that should equal 5 to the 1/4 to the 4 times e to the I pi over 4 to the 4. That equals 5 to the 1/4 times 4 is 5. E to the I pi over 4 times to the fourth is e to the I pi. That is in fact equal to -5. So check. We have found one of the fourth roots. Okay. So now what we want to do is we know that we're looking for the four fourth roots, and we know that they are each 1/4 of the way around the circle from each other. So a full circle is 2 pi. 2 pi is a full circle. Divided by 4 gives us 1/4 of a circle, so that's pi over 2. So this is equal to the angle between roots. Okay? So that means that the second, third, and fourth roots, second fourth root, third fourth root, and the fourth root. I have to be very emphatic about what I'm doing here. It's not like I'm finding a third root or a second root. These are all fourth roots in the sense that I would write a radical sign and put the little 4 in the crook of the radical sign. So what I'm saying is that there are 4 such roots. I already found the first of them up here. I'm finding the second, third, and fourth of these fourth roots. It's just a sort of confusing multiple use of these ordinal numbers as I speak. So, all right, so the second one is going to be, it's going to have the same radius, 5 to the 1/4, times e to the I. We start with pi over 4. In other words, that's where the first of the roots was. And now we're going to add this angle. So it's going to be plus pi over 2. This one is going to be, again, the same radius, 5 to the 1/4. It's going to be e to the I pi over 4 plus 2 times pi over 2. And this one is going to be 5 to the 1/4 times e to the I pi over 4 plus 3 times pi over 2. So this is going to be 5 to the 1/4 e to the I 3 pi over 4, 5 to the 1/4 e to the I 5 pi over 4, and 5 to the 1/4 e to the I 7 pi over 4. And don't forget that we also had this first one here. So I'm just going to copy that and bring it down so that we can see all of the roots in one place. So this one, I'll just label it. This was the first fourth root, and that's there. And these are now the 4 fourth roots of -5. Now let me just show you where these exist on the complex plane. So here we've got 1, 2, 3, 4, 5, just barely reach it there. That's -5. So this was our original number. 5 to the 1/4 it's a pretty small number. It's a little over 1. So what we can see is that all the roots are going to lie on a circle that's quite a bit inward into the plane from the original number 5. Remember, we started with a radius of 5 for the original number. So we were asking what all the roots of -5 are. So we started with a radius of 5. And the first thing we did was we found this much smaller radius, 5 to the 1/4 power. And now looking at where these roots are, 5 to the 1/4 e to the I pi over 4. So that's going to be about there. And then all these roots are 1/4 of the way around the circle from each other. So they're going to be there, there, and there. That's what happens when we keep adding pi over 2. So this is 5 to the 1/4 e to the I pi over 4. This is 5 to the 1/4 e to the I 3 pi over 4. I won't keep writing them in, etc., etc. But we can see that they are all equally spaced angular-wise around the unit circle. They're all pi over 2 apart from each other around the unit circle. So there's the answer. And by the way, certainly far be it from me to predict what you might see on the exam, but I know that it's fairly common on final exams for there to be a problem, it sort of looks like this.